This is section 2.7, which deals with tangents, velocities, and other rates of change. Our first objective is to find the equation of a tangent line or a normal line to a curve at a given point. So we've got some vocabulary, and it's going to feel a little familiar because it's a lot like what we did in section 2.1. Our first vocabulary is tangent line, and the tangent line to the curve y equals f of x at the point P, A, comma, f of A is the line through P with this slope m equaling the limit of this difference quotient, provided the limit exists. So before we do the example, I want to take just a minute to kind of discuss what's going on here. If I have a general function, just any function at all, that is f of x, and we want to nail down a point A that has a y-coordinate f of A, then what this tells us is that we can pick a second point and label it x comma f of x and connect those two to create a secant line. And if I want to get the slope of the secant line, I would do y minus y over x minus x. So without the limit, this difference quotient right here is representing the slope of the secant line. And if you remember from section 2.1, we had to let those 2 points get closer and closer and closer to each other. Since I want the tangent line at the point P, it's the x that needs to be moving along the curve. So if I move this point x along the curve up to A, then eventually those 2 points are going to collide and we will get a tangent slope instead of a secant slope. Well, notice that this notation here that we learned in sections 2.2 and 2.3 is what enables us to get that x-coordinate of x to collide onto the x-coordinate of A. So if this limit actually exists, then this limit of the difference quotient is going to be the slope of that tangent line. So if we look now at example 1, we want to find the slope of the tangent line to the parabola y equals x squared at the point 2, 4. So what we've just done is we've said that y, which is f of x, is the same as x squared, and we have the point P, which is a comma f of a, is going to be 2 comma 4. So if we want to set up our tangent slope, m, it will be the limit as x approaches my a, which is 2, times my f of x, not times, but of my f of x minus my f of a, which is 4, over my x minus my a. So here's our generalized setup. We have the y-coordinate minus the y-coordinate over the x minus the x, and now we want those x-coordinates to be going to the same place. So we want x to collide with the 2 so that those 2 points become 1. So before we can simplify this, we first try and plug in the 2 and realize that we get a 0 on the bottom. So that's a problem. In order to fix that problem, we need to somehow create a factor of x minus 2 on the top. So to get there, we're going to use the actual function to help us write what f of x equals. If I plug x into f, I get an x squared. So I'll have an x squared minus 4 on the top and an x minus 2 on the bottom. Well, now I have created something that I can factor. So I'll have an x minus a 2 times an x plus a 2 over an x minus a 2. And we can see that those x minus 2's will cancel, and I can then compute the limit and get 4. So what does this tell us? It tells us that the slope of this curve at the point 2 is equal to 4. So if we look just at a picture here, here's that parabola that I've graphed, the x squared, and at the point 2, 4, I have a slope of a tangent line that equals 4. Turns out that there is yet another way to define the slope of the tangent line. They are interchangeable. However, you will find that in many cases this particular definition, though it looks a little more scary at first, is actually easier to work with. So if we look at our same function here, here's some random function f of a, and we pick a point A so that its y coordinates is f of a. then what this one tells us is that, again, we're going to try and find the tangent slope at the point P, only this time instead of labeling a second point as x comma f of x, we're going to let this point be h units away from a. So I'm going to add h to this value, and I'll get an x coordinate of a plus h and a y coordinate of f of a plus h. Now the goal is to get these 2 points to collide, so I need this point to scoot down along the curve until it runs into the a. Well, how that's going to happen is not by saying x approaches a, but by letting this distance h go to 0. So we can see here in that limit statement that as h shrinks down to 0, these 2 points will collide. And if we again look at the difference quotient, we can see the y minus the y over the x minus the x will end up giving us this, because I would have had an x minus an x, and notice that those a's are going to cancel, and we'll be left just with the f of a plus h minus f of a over 8. So let's look at example 1 again. We have the same function, that y equals f of x equals x squared. We have the same point P, which is a f of a. In this case ends up being 2 comma 4. Only this time we're going to set up our slope using the definition of the slope of the tangent line involving an h. So I'm going to write the limit as h approaches 0 of f of a plus h minus f of a over h. Then I'm going to plug my a in. So I'll have limit of f of 2 plus h minus f of 2 over h. Then I'm going to actually see what the outputs of the function are by plugging those values into the function. So if I plug a 2 plus h in for x, that means over on this side I'm going to have a 2 plus h quantity squared. And then I'm going to subtract what comes out of the function when I plug 2 in, which we saw already was 4. Now if I try to plug h equals 0 right now, I get a 0 over a 0, which is usually evidence of a hole. So in order to fix that hole, I need to be able to factor the top. And I'm not going to factor until I have expanded and combined my like terms. And the beauty of this particular method is that if you expand properly, you'll end up getting rid of every term on the top that does not have an h in it. So we can see on the top that the 4's and the negative 4 will cancel, leaving me with something that I can then factor. Remember, the goal is to get rid of that problem factor of h on the bottom. So if I factor the h out of what's left over, I have a 4 plus h. The h's will cancel. Now I no longer have an issue with h equaling 0, so I plug it in and I get a 4. Notice that that is the exact same slope we got when we did it the other way, and we have again figured out the slope that goes with this point 2, 4. It is going to equal 4. So let's remember that our objective is to find the equation of a tangent line or a normal line to a curve at a given point. And what we've done so far is find the equations, or not the equations, but we've found the values of slopes. So we now need to connect that slope to what we know about equations of lines to write the actual equations of the lines. So just as a quick recap, let's recall what we did in Algebra 1, in Geometry, in Algebra 2, which was, how do we write equations of lines? If we have a point, a, f of a, and we have a second point on our line, which is x comma y, and we know that the slope is m, we can rewrite that slope as rise over run, or the difference between the two y coordinates. So we'd have an x minus an, or excuse me, a y coordinate minus a y coordinate over an x coordinate minus an x coordinate. So we should remember this before we did anything involving limits or tangent lines or secant lines, any of that. We should remember that slope is our rise over our run. So what I'm going to do is I'm going to rewrite this expression by multiplying both sides by an x minus a. then it looks like that old point slope formula that you learned. And what we want to do is we want to have this set up so that we can always put it into our calculator and graph it really easily. So I'm going to move this f of a to the other side by adding it. And if we look, we can see that the general equation of the line will be y equals the slope that you compute times the x minus the x coordinate of the point you are given plus the y coordinate of the point you are given. And if you can remember this formula, then at any time you can write the equation of the line provided you know the slope, the x coordinate of a point, and the y coordinate of that same point. Now let's look at example 2 where we actually find the equation of the tangent line rather than just the slope. On this particular problem, we want to write the equation for the point 3, 2. So we know already and can write up at the top that y is going to equal some slope times x minus the x coordinate plus the y coordinate. We already have the point, we can put it in. All we're looking for now is the slope. And I'm going to recommend that you use the second slope formula, which is the h approaches 0. So we have the limit as h approaches 0 of f of a plus h minus f of a over h. I would recommend that you write the actual definition down first and then identify your a. So in this particular problem, a is going to be the x coordinate of the given point, which is 3. So we're going to be plugging a 3 plus h into the function, and we're going to be plugging a 3 into the function. If I plug a 3 plus h into the function, we have to recall how we used functions in courses that we've had already. Now remember that whatever is an x in the function gets replaced with whatever's plugged into the function. So if I plug a 3 plus h in for x, I will have a 4 over a 3 plus h plus a negative 1. If I then plug in a 3, I'll have a 4 over a 3 minus a 1, or a 4 over a 2, which is why this y coordinate here was a 2. And then over the bottom, I'm going to still have my h. If we look at this now, it looks a little more complicated than what we've had in the past. And I try to let h equal 0, I'll end up with a 2 minus a 2 on top, which is a 0, divided by a 0. So there's a 0 over 0, or evidence of a whole. So in order to fix the whole, I want to be able to factor. And looking at this particular problem, it's a little complex because I have a fraction over a fraction. So the first thing I'm going to do is I'm going to recall that dividing by an h is the same as multiplying by the reciprocal of h. And when I do that, I at least get rid of the complex fraction. The next thing I'm going to do is I'm going to remember that I cannot combine fractions unless I have the same denominator. So right now, on this first fraction, I have a 3 plus h minus 1. And on the second fraction, I just have a 1. So I'm going to make a very smart choice for 1 for both of those fractions so that I create the same denominator. So this one just needs a 1, whereas this one over here needs that 3 plus h minus 1. So I'm going to multiply both top and bottom of this second fraction by the factor that the first fraction had. When I do that, I end up with the limit as h approaches 0 of a 4 minus that whole top. And then on the denominator, I'm going to have the 3 plus the h minus the 1, and the 1, and the h. Still, h going to 0 is going to put a 0 on the bottom, which is problematic. So we're hoping that with our good algebra, we were able to create a factor of h on the top. If I look here, I have a 4 minus a 6 minus a 2h plus a 2. We'll notice that the 4 plus the 2 is a 6 minus the 6. All of those are going to cancel, which is very good for us because now anything that doesn't have an h in it on the top disappeared. And on the bottom, I now have an h that can be canceled. So on the top I have a negative 2 times an h, and on the bottom I have a 3 plus an h minus a 1 times a 1 times an h. Those h's can cancel, and now I no longer have an issue with h equaling 0. So I can plug in an h equals 0, I get a negative 2 on top, and on the bottom I get a positive 2. So that slope ends up equaling a negative 1. I now have the equation of the tangent line, and I am done. So let's try it now on example 3. Example 3 says, find the equation of a tangent line to this new curve at the point 16, 4. So again, we know we're going to be able to write y equals the slope, whatever that ends up equaling, times x minus the x coordinate plus the y coordinate. So when we're done, we're going to come back and put that slope up. So to get the slope, we backtrack to our definition, which is slope equals the limit. And again, I'm going to encourage you to use the h definition because it's a little easier to cancel out that h on the bottom than to cancel out an x minus a. So on the top, we have an f of an a plus h minus an f of a. And on the bottom, we have an h. Now we're going to use the function itself, which is this root of x, to plug in our a plus h. We're also going to use the fact that a is 16, f of a is 4, and root x is our f of x. So if I plug a plus h, we won't skip any steps here. My a is a 16 plus h, and my a is a 16. If I plug a 16 plus h into the function, I get a square root of a 16 plus h because I replaced this x with an 16 plus h. If I replace this x with a 16, I get the square root of 16, which is 4, or that y coordinate that was given to us. Again, if I plug h equals 0 in, I'm going to get a 0 on top, 0 on bottom. It's a hole. We got to fix it. So we fix it by making a smart choice for 1 that will get that h out of the radical on the top. So I'm going to multiply by a 16 plus h plus a 4 on both top and bottom. Use that conjugate. And now we'll simplify. Remember, the beauty of conjugates is that those middle terms disappear. So I get things out of the root minus that 16. And on the bottom, I'll have an h times that root 16 plus h plus a 4. So on the top, we can see that the things that don't have h's in them are going to cancel, which is a very good thing. And what's left is just an h over an h. Well, that's going to cancel as well and give me a 1 on the top. So we'll end up with the limit as h approaches 0 of a 1 over a root 16 plus h plus a 4. Now h equaling 0 is no longer a problem. Plug it in. I get a 4 plus a 4 on the bottom, which gives me a 1/8. And now I can go put in my slope. Example 4 is a little different than what we've done prior to this because we want to now determine the points on the curve that have a tangent line passing through the origin, as opposed to getting the points and then finding the equation of the tangent line. So I'm going to warn you that this is one of my favorite types of tangent line problems because it requires a bit more understanding of what we're doing as opposed to just plugging and chugging through a process that gets pretty routine after you've done it a few times. So in this particular case, since we do not know the points, we actually have to find the points that do things that we want them to do. So we're going to start off, kind of the process that we'll follow in order to do this is we'll begin with a generic point. And that generic point is just going to be a comma f of a, which in this case will be a comma 2a squared plus 1. And then we're going to find the slope that goes with that point. So we're going to use our general formula for the slope, which is that limit as as h goes to 0 of f of a plus h minus f of a over h, and we're going to plug it in and see what happens. So if I plug in an a plus h into this function, the x gets replaced with an a plus h. And I'll square it, multiply it by 2, and add 1. Then I'm going to subtract what comes out of this function when I plug in an a. Well, that's a 2a squared plus 1. Notice I put parentheses around that entire output because I need to subtract the whole thing. If I now multiplied or plugged in the h equals 0, I'll get 0 over 0, which is evidence of a whole. So in order to fix the whole, I need to distribute. Don't forget to double that middle term. And if I do this properly, I will end up canceling out anything that does not have an h in it. And you can see here that the 2a squareds are going to disappear and the 1s are going to disappear, and what I have left has an h in it. So I can now factor the h out of the top, and I'll have left a 4a plus a 2h, and these h's will cancel, creating something that no longer has an issue when I plug in 0. So if I plug in 0, I end up with a slope of 4a. Now that I have the slope and I have the point, I can write the equation of the line. The equation of the line will be y equals the slope times x minus the x coordinate plus the y coordinate. Now this equation of the line still has a's in it, so our goal is to figure out what value of a will make this line pass through the points 0, 0. So remember, equations of lines are just a way of writing a whole series of points, an infinite number of points, and each point that is on the line will satisfy this equation. So if 0, 0, or the origin, is on the line, then if I replace y with a 0 and I replace x with a 0, I will end up with an equation that is true. So now I have an equation that involves only a, and I can use my calculator to solve for a. So let's bring our calculator up, turn it on, go into your Y editor. No, actually just your home screen will work. We want to solve this equation right here. So we're going to go to our algebra menu, which is F2, and we're going to choose solve, which is the first option, and we're going to type this equation in. So that would be 0 equals 4 times a, so we'll do alpha a, times a 0 minus an alpha a, plus a 2 alpha a squared plus a 1. Now the syntax for solving is to solve the equation, comma, and you tell it what you want to solve for. In this case, we want to solve for alpha a. So then we close our parenthesis, finish the command, and hit enter. And we see that we have two different a values coming up. We have a root 2 over 2 and a negative root 2 over 2. So those are the x coordinates of the 2 points that work. So back on our home screen over here, we're going to write the points are now going to be root 2 over 2 and negative root 2 over 2. They're both going to work. To get the y-coordinate, since the goal was to determine the points, I need the y-coordinate that goes with it. I'll take this root 2 over 2 and plug it into the function. So if I plug a root 2 over 2 and I square it and then multiply by 2 and add 1, I'll end up with a 2 times a 2 over a 4 plus a 1. Well, this is going to simplify down to a regular 2. Notice that the negative, if I plug the negative one, I'm going to get the exact same thing because I'm just going to square that negative. So here I've got the 2 points whose equations of their lines are going to pass through the origin. And we can see that here if we graph. Here's our 2a squared or 2x squared plus 1. Here are the points that we found, and you can see that those tangent lines go beautifully right through the origin. We have one more example that goes with this objective, and that is involving normal lines. So we need to know that the slope of the normal line is the same as the slope of the tangent line, except you're going to do the opposite reciprocal because normal lines and tangent lines are perpendicular to each other. So in example 5, we want to find an equation of the normal line to the curve at this point if y equals this kind of complex fraction. It's going to be rough, but we'll get through it because we have lots of algebra skills. So first we're going to write down that no matter what, when we're trying to write an equation of a line, we need a point and we need a slope. So we've got this point a, f of a, which in this case is going to be a comma a minus 1 over a minus 2. And then we need the slope that goes with that, which in this case is going to be 1 over the tangent slope. So we're going to come back to this after we have found our tangent slope. Once we have the point and the slope, we're able to put them into the equation, which will be y equals a slope times x minus an x coordinate plus a y coordinate. So our equation of the line is going to have a bunch of a's in it, and that's okay. We just have to kind of keep everything straight. So let's find the tangent slope first using our definition. Remember that definition is the limit as h approaches 0 of f of a plus h minus f of a over h. So I'm going to plug in a plus h into my function. If I plug in a plus h in, I will replace these x's with a plus h's. So I have an a plus an h minus a 1 over an a plus an h minus a 2. Then I'm going to subtract what comes out when I plug in an a. So those x's will get replaced with a's. So an a minus a 1 over an a minus a 2. And then on the bottom, I still have this h. So I've replaced f of a plus h with what it equals, and I've replaced f of a with what it equals. Now looking at this, it's pretty darn complicated. So I'm going to use that trick that I used before, which is dividing by h is the same as multiplying by the reciprocal of h. And then I'm also going to be looking for a common denominator for these two. So don't drop the limit because I haven't computed the limit yet. I'm going to have the tops times that reciprocal of h. On the top I have an a plus an h minus a 1 over an a plus an h minus a 2, and then I'm going to subtract an a minus a 1 over an a minus a 2. I left some space here because I'm going to make smart choices for 1 that will create a common denominator. So this particular fraction is missing the factor a minus 2. So I'm going to multiply by an a minus 2 on both the top and bottom. Over here, I'm going to multiply by this factor because this is the one that is missing. So pretty messy, but if we keep things straight and write neatly, we aren't going to miss any of the pieces. So now we want to simplify, because our whole goal, what's driving this process, is we've got to compute the slope so we can take its opposite reciprocal so we can get the equation of the normal line. So right here we're kind of bogged down in the algebra of trying to compute that slope, and h equaling 0 is not an option because I'll be dividing by 0. So if we do all of our algebra correctly, we'll end up with a top where everything that doesn't have an h in it cancels out. So if that doesn't happen, we know we made a mistake. So let's start multiplying through here. We have on the bottom, we're going to leave it as is because we want to be able to see that problem factor of an h coming out. So remember, we're going to combine our common denominators, so we just get the denominator showing up one time, and on the top we'll have this minus all of this. So I'm going to distribute, but I'm not going to try and distribute this subtraction all the way through. So I'm just going to be multiplying here. And when I do that, I'm going to do the first one times both of these, and then I'll move to the second one times both of these, and then the third one times both of these. So that a, when I distribute, gives me an a squared minus a 2a. Come on. Minus a 2a. The h, when I distribute, gives me an ah minus a 2h. And the negative 1, when I distribute, gives me a negative a plus a 2. So there's my first two parentheses multiplied out. And now I've got to multiply the next two, and I'm not going to distribute that minus through until I'm all done. So first thing is the a. I've got to give it to all three of these. So I'll have an a squared plus an AH minus a 2A. Then I'm going to distribute the negative 1 to all three. So that's a negative A, a negative H, and a positive 2. So now that I have everything multiplied out, I'm going to start looking to see what cancels. And if I did it correctly, everything that doesn't have an H in it will disappear. So here's an A squared, and we can see that I'm going to subtract an A squared. So that's good. That disappears. Here's a negative 2A, and here's minus a negative 2A. So that disappears. Here's an AH. Well, it turns out I have one of those, so even though it's got an H in it, it's still disappearing. I have a negative 2H minus a negative H. Okay, so that one's going to remain. So let me write that one down. I have a negative 2H minus a negative H. That's a negative 2H plus an H gives me a negative H. So now I've finished that one. Now I've got a negative A, and I'm subtracting another negative A, and I have a 2, and I'm subtracting a 2. So the only things that were left were this negative 2H and minusing a negative H, which I've already taken care of. Everything else disappeared. And notice on the bottom that I still have that A plus H minus 2, and an A minus a 2, and an H. So what's nice is that these H's now cancel, and I have a negative 1 on top, and I can compute the limit because I've eliminated the problem that was creating that division by 0. So I can plug in my H equals 0, which means I don't have to write the limit anymore, and I'll get a negative 1 over an A minus a 2 times another A minus a 2. So I've now computed my tangent slope. So the normal slope is the opposite reciprocal of that one. So I'll change the sign and flip it. Now that I've got the slope, I can go plug it into the equation for the line, and I'm done. So work on those 4 web exam problems that go with your notes and see if you can then write the 3 things you have to find before you can write the equation of a tangent line to a function.